مرحبا، معكم مهندسة تمارا. اليوم بدنا نشرح عن piping and instrumentation diagram. This video is a continuation of another YouTube video. I'm sure the link is in the description below. So piping and instrumentational diagram, هم ال P&IDs. First, we're going to talk about the types of time. Of course, we know that P&IDs contain control loops. هذول control loops, they have different purposes. So today we're going to talk about the types of control loops and an example on each type of control loop. The type of control loops are temperature, pressure, flow, concentration, and level. Of course, when we draw control loops or we draw P&IDs, we use the Visio program. For now, if the next examples, we are not going to physically write and do the Visio. So if anybody wants the Visio parts to be done, please comment below. The first example we're going to talk about is compressors. Now, a compressor is an equipment used on the gas phase streams to increase its pressure. That's well known. The main parameter in this case is the pressure. So if the main parameter is pressure, that means the control loop that we're going to add on the compressor is, of course, a pressure control loop. Now, in this, I'm going to explain it here. For example, we have a compressor. We will have a PI, a PT, and a PNIC. What are those? PI is pressure indicator, PT is pressure transmitter, and PIC is pressure indicator controller. Now, in this example, we have the compressor. The stream, the gas stream leaving the compressor, we will install a PI on it. The indicator, the pressure indicator, will indicate the pressure leaving the compressor. It will send an electric signal. This dotted line is an electric signal to the PT, which is the pressure transmitter. And the transmitter will also send electric signal to the pressure indicator controller. Now, the pressure indicator controller will send a pneumatic signal to the motor of the compressor. It will order it. For example, if the pressure leaving is way too high than the design pressure, it will order the compressor motor to decrease its efficiency, and vice versa. So in this case, we have a pressure control loop, PI, PT, PIC. The next example is an heat exchanger. Of course, a heat exchanger is an equipment used to heat or cool a process stream. In the heat exchanger, we have a shell side and we have a tube side. In the shell side, it's mostly the utility that I'm using. If I'm heating, I'm using steam. If I'm cooling, I'm using cooling water, and so on. So the main parameter when it comes to heat exchanger is obviously temperature. This is an example of a heat exchanger. We have a heating fluid, and the heating fluid is leaving. So this is my utility, and this is my process stream. So I will add a temperature indicator on the process stream that will send electric signal to the temperature transmitter, and it will send another electric signal to the temperature indicator controller. Now, the controller will control the amount of flow entering the heat exchanger from the heating fluid or from the utility. So if the temperature leaving in the process stream is too high, that means the controller will decrease the amount of flow of utility entering the heat exchanger, and vice versa. So in this case, we have a temperature control loop, TI, TT, and TIC. Next, we're going to talk about a reactor, but not just any reactor, a reactor with a cooling jacket. Now, some reactors require a cooling jacket in order to keep the temperature inside the reactor at a required value, or for example, constant. Now, the temperature inside the reactor is connected to the flow of the cooling water that's fed to the jacket. We'll explain that in a second, and this will explain in a second. So for example, look at this. We have a reactor. This part is the cooling jacket, and we have cooling water inlet and cooling water outlet. This cooling water will keep the reactor at a temperature of a certain value. So we will connect the cooling water with the temperature inside the reactor. This is my temperature control loop when it comes to the reactor. So we'll put a temperature indicator connected to the reactor, temperature transmitter, temperature indicator controller, and same as the heat exchanger, the controller will control the amount of flow entering of the cooling water entering the jacket. And of course, these extra valves are just backup valves. On the reactor, and such a big equipment such as the reactor, we need more than control loop. One control loop isn't enough. So the second control loop is a flow control loop. Now, in a reactor, especially a reactor that contains catalyst, for example, the amount of flow entering or fed to the reactor must be at a certain value. So in here, we have the reactor, the flow entering it. So I will place a flow indicator, electric signal to a flow transmitter, electric signal to a flow indicator controller, and a pneumatic signal to a valve. This valve the controller will order the valve, whether if the flow is too high, it will decrease it, and if the flow is too low, it will widen its opening so more flow will enter the reactor. So in this case, the first control loop, we have the temperature control loop. And the second control loop we have is a flow control loop. The next example is absorber. An absorber has more exiting and entering streams, so which means it's going to need more than just one control loop. It has three control loops, actually. First, the pressure. Second is the level. And third and final loop is the concentration. I will explain them right now. Here's an absorber. We have the vapor feed. We have the liquid feed. We have the liquid out, and we have the vapor out. In this case, the first control loop is the pressure. Let's just choose the easiest. A pressure indicator is placed on the leaving vapor stream with a transmitter and a controller. It will affect or it will control the amount of flow leaving the absorber. So if the temperature increases, it usually means that there's a lot of vapor buildup in the actual absorber. So in here, the valve will just allow more flow to leave the absorber, therefore decreasing its pressure, and vice versa. The next second control loop we're going to talk about is a level control loop. Now, if I have a column that has both liquid and vapor in it, the liquid level must be at a certain height. It cannot exceed or decrease or be less than this height. So in here, we'll add a level indicator. Again, level transmitter, level indicator controller. It will control the valve of the liquid flow leaving the absorber. Now, this valve, if the level of the liquid is too high, so it will order the valve to release more liquid leaving the absorber, therefore decreasing the level, and of course, vice versa. The final control loop, and I think the most important control loop when it comes to the absorber, is the concentration control loop. Now, in an absorber, usually we're using a liquid to absorb, let's say, a vapor or a certain composition of a vapor. This way, we're using a solvent, usually DEA, NEA, whatever solvent we're using. This solvent entering here from the liquid stream must be at a certain concentration. And again, usually this solvent that we're using is being regenerated and used again. But this regenerated solvent is not enough, so we need the storage solvent, which is here. So the regenerated solvent and the storage solvent are mixed, and a new stream is entering the absorber. But this stream must be at a certain concentration. So what do? We add a concentration control loop. We add a concentration indicator, concentration transmitter, and concentration indicator controller. The controller will control the amount of regenerated solvent that's entering the mixer. With this flow control in here, the concentration is controlled at the output mixer. So for the absorber, we have a pressure control loop, a temperature control, level control loop, and a concentration control loop. Now that we're done with the examples, let's explain the alarms. What are alarms? Now, in some cases, some of the operating variables are critical cases. So they're very important cases, which means that the control loop it's enough, but it needs a backup. What is this backup? This backup is an alarm. The alarm is done or installed so that it will inform the site engineer that something's happening, that there's a setback, the temperature is increasing, the pressure is decreasing, whatever it is. An alarm is placed to inform the site engineer that something's going on with the control loop. We have two types of alarms, either high or low. An example of a high or low is a temperature, either temperature alarm high or temperature alarm low. So alarms are placed on a PNID. Where are they placed on the PNID? For example, we have this reactor PNID. The alarms are placed between the transmitter and the controller. In this case, we have it between a temperature transmitter and the temperature controller. In that case, we have it between the pressure transmitter and the pressure indicator controller, and so on. If there's any questions, we'll see you guys in the comments below. Thank you.